there's a new possibility, new way to do mathematics, yeah, which has a number of advantages. And this new way of doing mathematics is basically very close to just using a programming language. In mathematics, people do prove theorems. Yeah, I mean that's important activity of mathematicians, and there's a problem. Sometimes theorems turn out to be wrong. Yeah, so it's very embarrassing. I mean, people publish something and they provide a proof, but then there's something wrong with the proof. That happened lots of times, and now we have a new opportunity using computer science technology. We have something called interactive proof assistants. Yeah? And what you can do with those is you basically, with the dialogue with the computer, you produce a proof, a mathematical proof, which can be stored like a computer program. And it can be checked by this program or by another program to make sure that you haven't cheated. Yeah? So that's very cool. And it's sort of increasing use of this. There are actually some conferences where you can sort of submit an artifact, yeah, which is this formal proof, yeah, like this computer code which actually proves the theorem. And then people can check, and you can be very, very sure that, that your proof is correct. Yeah? So that's something which is happening. So in the moment, still doing these proofs on a computer is quite a big effort. Yeah? And it's harder, takes more time to do these computer-based proofs, but you get the benefit of being really sure that what you do is correct, yeah? And then other people, they can check it and they don't have to trust you. There's no need for lots of people. People are getting lazy these days, you know? You get all these referee requests, you think, oh, I can't read this proof, it's too much, I don't have the time, yeah? But now we have these computer systems, so one of them is called COC, it's a French system, and I think they called it a bit to upset English speakers. Yeah, I mean, I gave a lecture. I was giving a lecture on cock, and the students were always cringing and laughing or whatever. And I think it's really French revenge that they chose this name to make us English speakers embarrassed. Yeah. But anyway, so there are this possibility to do mathematics on a computer. And we could just do mathematics as has been done using something called set theory. Many people learn about sets and elements and this sort of thing. And just formalize this. But I think if we would do this, we really miss an opportunity. Yeah? This COC system, for example, is actually based on a programming language. It's a programming language called type theory. Okay, so this type theory is at the same time a programming language, and it's a logic, so you can do logical reasoning, and it's a replacement for this language mathematicians use called set theory. There was a famous mathematician, German mathematician, yeah, called Cantor, who came up with this idea of a set. A set is just a collection of things, like there can be numbers, there can be other things, whatever mathematical objects you want to organize, you can put into a set. Yeah.
So I'm my mathematics is a little bit rusty, but is this what we do when we're making Venn diagrams and things?
Yeah, Venn diagrams, right. This intersections, yeah, you can construct intersections of sets, unions of sets, and so on. So a set is just a collection of things, and you work with this. So what Cantor started was what we call naive set theory. And then this sort of evolved. There was a famous work by another German called Frege, who wrote something called the Begriffsschrift, the foundations of thought, of mathematics. He wanted, so the goal was to put firm foundations under mathematics. Yeah? And he developed this system, wrote this book, but then he got in trouble because an English mathematician, Russell, discovered that there was something wrong with his system, and that's a very famous paradox. It's about the set of all set which do not contain themselves. Yeah? And in Frege's system, you could construct this set, but then the problem is, does it contain itself? No, if it contains itself, it should not contain itself. If it doesn't contain itself, it should contain itself. So the whole building Frege built sort of collapsed, yeah, and he was very depressed about this. Yeah. But then later, in the 20th century, early 20th century, again, German mathematicians fixed this whole thing. Yeah. It's Zermelo. He developed a system of axioms, basic assumptions about sets, which appeared to work, and then Fraenkel added one more axiom, which was sort of missing. Yeah? And this system, called Zermelo-Fraenkel set theory, is considered the foundations of mathematics, yeah, since the 1920s. So actually most mathematicians, if you ask them, they're not really, they couldn't tell you the axioms. Yeah? They don't bother. This is the foundations. That's what we do. Yeah? Now, type theory is different. It's not based on set theory. Yeah? It's a more recent development, going back to the 70s, where a Swedish mathematician and philosopher, Per Martin Löf, he wanted to capture what is called constructive mathematics. Yeah? By constructive mathematics, we mean that we can actually always obtain a result. Yeah? That we don't just claim, for example, if you have a function, you may have no way to calculate the answer. Yeah? In constructive mathematics, there's always a way to obtain an answer. If you say there exists a number with some property, in classical mathematics, you may not know the number. Yeah? In constructive mathematics, you can only make this claim if you can actually provide a number, a concrete number. Yeah? And Per Martin Löf, he did nothing to do with computer science. I mean, he was really a philosopher, a mathematician, very interesting guy. But then people thought, okay, this idea of always you get an answer, doesn't this correspond to writing a computer program? He said, yeah, it's like a computer program. And this has been made more precise and has been used. So people started basically to write, implementing on a computer this type theory. Yeah. Type theory uses the types we have in programming languages. So type, like for example, the type of booleans, or the type of integers, or the type of functions from integers to booleans. So input is an integer, output is a boolean, and so on. So these are types. And a very important observation is that we can use types also to model logical reasoning, to model logical propositions. Yeah? So if you have a proposition, expression in the logic, I mean, for example, there are infinitely many prime numbers as a proposition, yeah? Or every two numbers, natural numbers, one is less than the other, or they're equal, or one is greater than the other. These are propositions. Yeah? And the observation is that we can, for every proposition, we can associate a type. And that's the type of evidence or proof for this proposition. Yeah? This is called the Curry-Howard equivalence. Yeah? So whenever you have a proposition, you find a type such, if there is a program of this type, then you know this proposition holds. So if you look, for example, if you have a proposition called conjunction P and Q, what's the evidence for it? It's a pair of evidence for P and evidence for Q. It's like a record. Yeah? It has got two components, one there, one there. Very, very simple. Yeah? Another example is if you have something like, let's say, we say for all natural numbers, let's say, it's the case, or for all pairs of natural numbers, so two numbers, m and n, it's the same whether we add m plus n or n plus m. So these two are equal.
You can flip it around. Yeah. Is it commutative?
Commutativity it's called, yeah. So now, the program for universal quantification is also a machine. It's a program, You feed it two natural numbers, and it outputs a proof that the two sums are equal. So basically we can translate logical proposition into types, yeah? And then proving a theorem just means we write a program which has this type. So that's what we call the Curry-Howard equivalence, yeah? And that's one of the main building blocks of type theory.
Okay. So this is computing basically getting its elbows in and getting stuck into some mathematics.
Yes, and I would say, okay, there is using type theory, it's very natural to do it on a computer, whereas set theory seems to be like rather alien to using computers. Yeah, it's in set theory, for example. There's also the notion of a function, but it's a derived concept. So you see, you have like a set of pairs which have certain properties. There's not this idea in type theory that a function is something where you put something in and you get something out, which comes from computer science, or which corresponds to how we think in computer science. Yeah? So a function in type theory is something we can actually compute with, whereas a function in mathematics and in set theory is something like just a set of pairs of all the possible inputs with corresponding outputs. But a function in mathematics may be something you cannot compute. Yeah? So I'm always saying, this is not a good name, then call it a function, because a function which doesn't function shouldn't be called a function. So, I mean,
dysfunctional function.
Yeah, the dysfunctional function. Type theory has got some other interesting features which have been discovered or made explicit more recently. And this is work which was started by a mathematician, actually. He's called Vladimir Voevodsky, and he's a field medalist at the Institute for Advanced Study in Princeton. He's doing something called homotopy theory. So homotopy theory is a quite abstract area of mathematics, where you try to understand of geometric objects, very abstract geometric objects. Yeah. And you basically identify geometric objects which you can transform like plastic or Play-Doh, yeah, which you can transform one into the other in continuous transformations. Yeah. And first of all, that doesn't seem to be anything to do with this type theory I mentioned. But Vladimir Voevodsky observed that actually there's a close connection between type theory and homotopy theory, which leads to this new idea which is called homotopy type theory. And so the idea here is that when in type theory you prove that two things are equal, this is like having one of these surfaces and having a path between these things. Yeah? And then you can also ask yourself, when are two equalities equal? And then you have a sort of a path between paths, a continuous transformation of paths. Okay,
it's getting quite abstract now.
It's getting very abstract.
Is this like are these Play-Doh objects a bit like a kind of way of visualizing these ideas, or is that what he's discovered?
No, it's not really. It's rather surprising, because we start with something which I call type theory, which is a programming language, and there's a logic, as I have explained. Yeah, and then there is this homotopy theory, which has completely different roots in what's called algebraic topology. Which is like, I mean, topology is the idea of describing continuous phenomena, like real numbers and surfaces and so on, which are important in physics and so on. And then in homotopy theory, people did it more and more abstractly. You know, they tried to distill the essence of these objects. You know, they're infinitely dimensional. No really good intuition for what's going on. Yeah. But then the surprising thing, and this is one of these surprising reuses of mathematics, yeah, that you go completely abstract in one direction and you come out somewhere completely different. Yeah. And this is the relation between type theory and homotopy theory. Okay. So it's not very direct. It's not like we have a type and then we have a picture which corresponds to this type. It's not like this. Yeah? It's much more indirect, yeah. But the mathematical principles underlying this homotopy theory and in type theory, they match up surprisingly well. Maybe a good question is, what is the payoff? Yeah, I mean, what does this buy us? And I think there's some very exciting opportunities now where type theory shows its sort of superiority over set theory. And this has to do with abstraction. If you want to build large mathematical libraries, yeah, you have to climb the ladder of abstract reasoning. Yeah? You don't want to do everything on a very concrete level, you have to do things abstractly. That's the power of mathematics. Type theory, and especially homotopy type theory, in its very structure is designed in a way that you cannot talk about the details of how things are actually implemented. So example, natural numbers. Yeah? In set theory, natural numbers are sets. That's maybe surprising. But in set theory, everything is a set. So natural numbers are sets. And there's a particular encoding of natural number using sets, using these curly brackets. Yeah? Or there's more than one. So you can use sets to encode natural numbers in various ways. Yeah? So for example, in the standard encoding in set theory, there's a very strange artifact. For example, one number is element of a bigger number. So if you think of natural numbers, counting numbers, it's true that 2 is an element of 3. Doesn't really make any sense, right? It's just the way it's set up. And which means when you work in set theory, you can see the implementation details, how numbers are actually represented using curly brackets. And that's something which doesn't really matter when you think about numbers. That's something like 2 is element of 3 is silly. Yeah? But you can't hide this. In type theory, when you introduce natural numbers in type theory, you cannot talk about the encoding, how they're actually represented. So for example, numbers are often represented following an idea of an Italian mathematician called Peano, who said 0 is a natural number, and if you have a natural number, then the number plus 1 is also natural numbers. And that's the way we can build our natural numbers. But there are other ways to do this, right? So this is when you write numbers in the system, they become very long, right? Because you write plus 1, plus 1, plus 1, plus 1. So that's not a very good system. So what we rather like to do is using binary encoding of numbers, yeah? Using 0 and 1. I mean, that's much shorter. I mean, it's still longer than decimal, but it's much shorter than this plus 1, plus 1, plus 1. And these are two ways of encoding the natural numbers. Now, in type theory, you cannot express a difference between these two encodings because they are actually, in a way, the same. They exhibit the same concept. So you automatically hide implementation details. Like, that's what we want to do in computer science. We want to hide implementation details because, like, if you want to change one implementation for another, you don't want to go all up, everything which uses this has to be rewritten. You want to say, okay, I just plug something else and it works. Yeah? So you want to be able to plug in, when you use the Peano numbers, and you think, oh no, it gets too cumbersome. I now plug in my binary numbers. And nothing should change. And that's how type theory is designed. And from this homotopy type theory comes a very important principle, which is called the univalence principle. And it basically says that two things which are equivalent, like the binary numbers and the unary numbers, the Peano numbers, then they are equal. Yeah? So we cannot talk about implementation details, but because we cannot talk about implementation details, two things which behave the same from outside are actually considered to be the same.
Is this changing massively the way people think about things in other areas then?
Yes, so let's say it has the potential of doing this. Yeah? So homotopy type theory has been suggested as a new foundation of mathematics. And it's exciting from a computer science point of view because it's a programming language. It's very close to, people can just move into it. They can learn logical reasoning and abstract mathematics just coming from this programming angle. So I think there is an exciting opportunity. And I think, looking back to set theory, we have these new tools of proof assistance to do interactive proofs. And in a way, it would be a shame if we use this new technology to formalize the mathematics from the 20s and 30s, the mathematics of, let's say it, yesterday. But there is an exciting new opportunity here to use to really use new mathematical idea, new foundations when we move and when we formalize mathematics.
We've got a value here at x1, and we're going between x0 and x1. And the value of y at this position
in type theory means you can prove excluded middle for this particular predicate. You can prove for all numbers either prime of n or not prime of n.